Pyrazole. It is a 5-membered heterocyclic ring system containing 2 nitrogen atoms. The molecular formula of pyrazole is C3H4N2. It is a heterocyclic compound characterized by a 5-membered ring of 3 carbon atoms and 2 adjacent nitrogen atoms. So the 2 nitrogen atoms are in 1,2 position. So pyrazole is a solid. It has a pyridine-like smell. It has a bitter, pungent smelling compound. It is soluble in water, alcohol, ether, and benzene. It has a melting point of about 66 to 70 degrees centigrade. It is toxic to eyes, skin, respiratory tract, and it has a stimulating effect. These are some physical properties of pyrazole. The term pyrazole was given to this class of compounds by German chemist Ludwig Knorr in the year 1883. So pyrazole is a weak base. Pyrazole is a weak base with a pKb 11.5. So if we compare, this is Pyrazole ring system, 5-membered heterocyclic ring system containing 1 nitrogen atom. So pyrazole is a 5-membered heterocyclic ring system containing 2 adjacent nitrogen atom in 1 and 2 position. So imidazole, it is a compound having same molecular formula as that of pyrazole, but the 2 nitrogen atoms are in 1,3 position. This is also, imidazole is also a 5-membered ring system. This is pyridine, which is a 6-membered ring system containing 1 nitrogen atom. If we compare the basicity of these compounds with each other, pyrazole, it is less basic compared with pyrazole. Pyrazole is less basic compared with pyridine, and pyridine is less basic compared with imidazole. So imidazole is more basic among all these nitrogen containing heterocyclic compounds. So among pyrazole and imidazole, imidazole is highly basic. Next comes pyrazole and then pyrazole. And if we compare the basicity of imidazole and pyridine, imidazole is more basic compared with pyridine. Coming to the methods of synthesis. Pyrazole has been prepared by 4 different methods. So the first method is Knorr-pyrazole synthesis. In this method, 1,3-dicarbonyl compounds react with hydrazine or phenylhydrazine to form 3,5-disubstituted pyrazoles. So for example, acetylacetone and hydrazine gives 3,5-dimethyl pyrazole. It is a condensation reaction. So first hydrazine reacts with one of the 2 carbonyl groups, and then the nitrogen atom will attack as a base in the ring closure reaction, resulting in the formation of a 3,5-dimethyl pyrazole. Next, suppose if the diketone is unsymmetrical, so unsymmetrical beta diketones gives a mixture of isomeric pyrazoles. That means these 2 isomeric pyrazoles differ in the position of methyl and phenyl. So this is benzoyl acetone. It is a beta diketone which is unsymmetrical. It is reacting with methyl hydrazine to form 1,3-dimethyl 5-phenyl pyrazole. So 1,3-dimethyl 5-phenyl pyrazole, and this is 1,5-dimethyl 3-phenyl pyrazole. So two isomeric compounds are obtained when the beta diketone is unsymmetrical. So the second method of synthesis is from the alpha beta unsaturated carbonyl compounds. So pyrazoles are also synthesized by the reaction of alpha beta unsaturated aldehydes with hydrazine and subsequent dehydrogenation. First, a condensation product is formed, which then undergo dehydrogenation to form the pyrazole ring system. So this is another example. So this is an alpha beta unsaturated ketone. It is reacting with phenylhydrazine in ethanol. So first the carbonyl group reacts with phenylhydrazine to form a hydrogen. Then this nitrogen atom will attack as a base. It will attack as a base at this carbon atom and ring closure will take place. So this nitrogen will attack this carbon atom. So hydrogen first loses this hydrogen and chlorine as HCl, and in the resulting compound this nitrogen atom will attack this carbon atom of the triple bond in the ring closure reaction to form a tri-substituted 1,3,5 triphenyl pyrazole. So therefore pyrazole can be prepared by the reaction of alpha beta unsaturated carbonyl compounds with hydrazine. Next, another popular method of synthesis of pyrazoles is the 1,3-dipolar addition reaction. So this is a classical method developed by German chemist Hans von Hechmann in the year 1898. So in this method, pyrazole was synthesized from acetylene and diazomethane in a 1,3-dipolar addition reaction. So the diazomethane and acetylene undergo a 1,3-dipolar reaction to form pyrazole. So simple diazomethane is reacting with a unsubstituted acetylene. So this is another example where a substituted acetylene. So diethyl acetylene dicarboxylate is reacting with a diazoacetic ester to form 3,4,5 tri-substituted pyrazole. So this is also a reaction between an alkyne and a diazo compound. Next. Similarly, another example. Propargyl aldehyde reacts with diazomethane to form 3,4,myl pyrazole. So this reaction also involves 1,3-dipolar addition reaction. So there is one more method of preparing this pyrazole ring system, which is substituted. So 3,5-diphenyl 1H pyrazole is produced when trans 1,3-diphenyl propene proptuene 1-one is reacted with hydrazine hydrate in presence of elemental sulfur or sodium persulfate, or by using hydrogen 1. So the hydrogen 1 reacts with the 1,3-diphenyl propene 2-ene 1-one. So in this reaction a side product is also formed. Azine is formed as a side product, and here we are getting a substituted pyrazole. So 3,5-diphenyl pyrazole is obtained in this reaction. So 1,3-diphenyl propene 1-one reacts with a substituted hydrogen or hydrogen. So coming to the reactivity, these are 4 methods of synthesis of pyrazoles. Next, coming to the reactivity. So the first one is alkylation reaction. So alkylation of free NH group of pyrazole proceeds with alkylating agents such as alkyl halides, dimethyl sulfate or diazomethane. So alkyl halides, dimethyl sulfate or diazomethane. These are some of the alkylating reagents that can replace this NH hydrogen. NH hydro hydrogen. NH hydrogen is replaced by the alkyl groups. So substituted pyrazoles undergo alkylation to give a mixture of isomeric products. This is because pyrazole has two isomeric structures. So where there is a change in the position of this hydrogen. Here hydrogen is on the N1. Next we can write another isomeric structure where hydrogen is on the other nitrogen atom. Therefore alkylation can occur at this hydrogen or this hydrogen. So this hydrogen can be replaced by alkyl group or this hydrogen can be replaced by the alkyl group. So this 3,5 disubstituted pyrazole when treated with methyl iodide, it forms a isomeric mixture of two methylated compounds. So here we have CH3 replacing hydrogen, and here we have CH3 which is replacing this hydrogen. So alkylation occurs at the NH. Next, electrophilic substitution. So pyrazoles are subjected to electrophilic substitution and the attack usually occurs at position 4. So the evidence for this is the resonance structures of intermediate cation. So let us see. These are some reactions of pyrazole. So unsubstituted pyrazole can undergo nitration to form a 4-nitropyrazole. So electrophilic substitution, NO2 is substituted as a electrophile at the 4th position. Similarly, sulfonation results in the formation of pyrazole 4-sulfonic acid. This is also another electrophilic substitution. Similarly, bromination occurs at the 4th position when treated with bromine acetic acid. Pyrazole forms a 4-bromopyrazole. So all these are examples of electrophilic substitution reactions, and we can see the resonance structures when electrophile attacks at different carbon atoms of the pyrazole ring system. So when the electrophile attacks at C3, so attack of electrophile at this carbon atom. Next, attack of electrophile at the 4th carbon atom. And this is attack of electrophile at the 5th carbon atom. So of this, attack at C4 is preferable. So nucleophilic substitution. So coming to the nucleophilic substitutions. So normally in nucleophilic substitution reactions, a leaving group is displaced by the nucleophile in the pyrazole ring system. So 5-chloro-4-nitropyrazole on treatment with amine gives corresponding 5 substituted product. This is an aromatic nucleophilic substitution reaction. Halogen atom in the position 5 is displaced by the amine. So this halogen atom is the leaving group. It is displaced by the base, this amine. So nitrogen will attack as a base at this carbon atom, and then after loss of H plus, it forms the 5 substituted product. So therefore, this is a nucleophilic substitution reaction. A leaving group present in the pyrazole ring system is displaced by the amino. So next, coming to some oxidation and reduction reactions. So pyrazole ring systems are normally unreactive towards oxidations. However, oxidation with peroxy acids gives the corresponding N oxide. So when 1-methyl pyrazole is subjected to treatment with hydrogen peroxide, it forms a 2N oxide. So oxidation with alkaline KMnO4. So alkaline KMnO4 oxidizes the alkyl side chain at the alkyl side chain to the carboxylic acid. So the alkyl side chains which are present in the pyrazole ring system is oxidized by the alkaline KMnO4 to the corresponding carboxylic acid. So we get pyrazole 3 carboxylic acid. Next, some examples of reductions. Catalytic reduction of 1-phenyl pyrazole yields both 1-phenyl pyrazoline and 1-phenyl pyrazolidine. So first two hydrogen atoms are added in the first reduction. So in the reduction over hydrogen and palladium at 20 degrees centigrade, one double bond is hydrogenated. This double bond, 4-5 double bond is hydrogenated to form a 1-phenyl pyrazoline. So on further reduction at 80 degrees centigrade with hydrogen and palladium results in the formation of 1-phenyl pyrazolidine. So the other double bond is also hydrogenated. So this is a completely hydrogenated pyrazole ring system. These are some important reactions of pyrazoles. So occurrence and importance. So in 1959, the first natural pyrazole, so 1-pyrazolyl alanine, was isolated from the seeds of watermelons. In medicine, derivatives of pyrazoles are widely used. The pyrazole ring is found within a number of pesticides, fungicides, insecticides, and herbicides. So there are many examples of pesticides, fungicides, insecticides, and herbicides where pyrazole ring system is a part of the complex structure. So similarly, chlorofenapyr, penpyroximate, pipronyl, tupenpyrad, and other compounds are used as pesticides, fungicides, insecticides, and herbicides. So pyrazole moieties are listed among the highly used ring systems for small molecule drugs by the US FDA. So notable drugs containing pyrazole ring are Selectroskip or Celebrex and the anabolic steroid stanozolol. So this is the structure of this Selectroskip. So here we can see the pyrazole ring system. So this complex structure contains this pyrazole ring system. So that thus this pyrazole ring plays a important role in the synthesis of many drugs and agriculturally used compounds such as fungicides, insecticides, and herbicides. This is about the pyrazole, physical properties, synthesis, and reactions and importance of pyrazole ring system.